Hello class, welcome to the Stat 511 Week 4 video on probability distributions. In this video, we're going to focus on 7 objectives. To begin, we are going to define what is a probability distribution and then start examining the properties of discrete probability distributions. Our next 3 objectives focus on specific type of discrete probability distributions, such as the Bernoulli process, the binomial distribution, and the Poisson distribution. Our 5th objective will be to examine the properties of the continuous probability distributions, and then our 6th and 7th objective will examine 2 specific continuous probability distributions, that is the continuous uniform distribution and the normal distribution. You're going to want to pay special attention to the normal distribution. It is a very important distribution in statistics. So to begin our understanding of probability distributions, let's recall the definition of a random variable or phenomenon. That is, it's a rule that assigns a numerical value to an outcome of interest. And we classify these random variables as either discrete or continuous. We use random variables to form probability distributions, which is a definition of the probabilities of all possible values of a random variable for an experiment. Some of these distributions arise frequently in our applications and our problems and in real life. And so what we've done as mathematicians, statisticians, is that we have given these distributions names, we've learned their patterns, their formulas, and their specific properties. So for our properties of our particularly our discrete probability distributions is that the probability still exists between 0 and 1 inclusive. The summation of our probability distribution should be equivalent to 1. And as this is a discrete probability distribution, that implies that all of the random variables are discrete. Some examples of discrete probability distributions is the discrete uniform distribution, the Bernoulli distribution, the binomial distribution, and the Poisson distribution. There are other ones, but these are the ones that we're going to focus on in this course. Actually, that's kind of a lie. I'm not going to focus on the discrete uniform distribution. Instead, I've chosen to focus on the continuous uniform distribution. But the Bernoulli, the binomial, and the Poisson are kind of the big 3 in discrete probability distributions, and those are the ones we focus on in this course. So let's start by talking about the Bernoulli process. And in this process, for Bernoulli, it really focuses on this idea of success and failure. So if you think about it logically, in many applications, there are just the 2 outcomes, success and failure. Particularly if we're, say, an assembly line or a manufacturing process, your product is either not defective or defective, which means it's either a success or a failure. Now, something that is interesting to understand about this concept of success and failure, success doesn't always necessarily mean it works when we're talking about statistics. A lot of time what we mean by success is it's the parameter that we're interested in. So if we're examining parts coming off an assembly line, chances are we're going to be more concerned about the defective parts because we're expecting things to work. If something's defective, that means we need to take action and there's a problem. So as that is our parameter of interest, when we are looking at formulas, it's our success. So there are 4 things you do need to know about the Bernoulli process. First, it is an experiment consisting of repeated trials. Each trial results in an outcome that may be classified as a success or a failure. 3, the probability of success, which we denote by a small case letter P, must remain constant from trial to trial, and that these repeated trials must be independent of each other. Each individual trial is called a Bernoulli trial, and together Bernoulli trials. So let's take a look at an example to really understand this. And as I already mentioned before, one big place where Bernoulli trials has a real life application is in the situation of manufacturing. So let us consider the set of Bernoulli trials where 3 items are selected and inspected at random from the manufacturing process. Our parameter of interest in this case, which we'll define as success, is a defective item. Our probability of having a defective item in this case is going to be 1/4 or 0.25. In our case, so we're going to let x equal the number of successes. Below, I've included a chart that lists all of our possible outcomes, aka our sample space, and its corresponding x. Remember, that's our number of successes, which means for every x should correspond to one letter D in the outcome. And if you notice for our x's, everything was either a 0, a 1, a 2, or a 3. That is going to form the basis of our probability distribution. So once again, from our previous slide, I've included that outcome and x chart. Now we're going to calculate the probability of each of our outcomes. Now, because we are dealing with independent trials, we can use our formula for calculating the probability of independent events. So that is that the probability of A and B equals the probability of A multiplied by the probability of B. In this case, it is 3 trials, so the extension would be the probability of A and B and C equals the probability of A multiplied by the probability of B multiplied by the probability of C. So you'll notice that I've only calculated the probability for 4 outcomes. That's because thanks to the commutative rule for multiplication, the event that is D, N, 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 D, N, and N, N, D is going to be equivalent, but it is going to occur more times. So, in fact, it's going to occur 3 times. So using our knowledge of probability, we can make our probability distribution, which is what I have now boxed. Notice we have our first row, which is our value of x's, and then our f of x, which is its corresponding probability. So the probability that there are 0 successes is 27/64, 1 success, 2 success, and 3 success with their corresponding probabilities. And as I said already, but I like to repeat things, that box is the probability distribution. So now that we've taken a look at the most basic of the discrete probability distributions, let's start looking at the binomial distribution. And this has a natural extension to the Bernoulli trials. So a binomial random variable is the number x of successes in n Bernoulli trials. So the binomial distribution is the probability distribution of a binomial random event. For this case, we like to denote the probability of x equal to x to be a lowercase b, and then in parentheses, we have x semicolon n comma p, where n is the number of trials, p is our probability of success, and of course, x is our random variable of interest. So from our previous example, we might be interested in the situation where we had a success equivalent to 2, meaning there was 2 defective parts off the manufacturing process of the 3. We would write this as a lowercase p. Our sample size was 3, and our probability of success was equal to 4. And from our previous probability distribution, we know that the probability is equivalent to 9/64. But there is another way we can go about this. So let us suppose a Bernoulli trial has probability of success P and the probability of failure Q, which is equal to 1 minus our probability of success. Then the probability distribution of the binomial random variable x, the number of successes in n independent trials, is the binomial distribution, which is equivalent to n factorial all over y factorial in parentheses n minus y factorial multiplied by p to the x multiplied by q to the n minus x, where x is equal to 0, 1, all the way to n. This is how we can find the probability in a Bernoulli or binomial distribution. So once again, let's take a look at our example 1. We have the same chart that we've had before with the outcomes and our corresponding number of x's. And we noticed that there were 3 ways to get to have one success or one defective part. So suppose we want to find the probability of getting one success in any specific order, meaning the probability of n dn, that specifically, that one particular case was n over 64. But if we just wanted to know what is the probability of getting one success regardless of the order, that is when it is a binomial distribution. And we can use the binomial formula from the previous slide, and we can get the probability of 27 over 64. So just to clarify, so when we're curious about getting something specific in that specific order, that is the Bernoulli. When we're interested in the multiple trials, when we're not caring about that specific order, that's when we're looking at the binomial situation. So just to explore a little bit further, so as we stated from the previous slide, the probability of getting one success was equal to 3 multiplied by 1/4 to the first multiplied by 3/4 to the second. Now, at this point, you may be wondering how exactly did that come about? Well, if we think back to our previous slide, it was n factorial all over y factorial multiplied by, in parentheses, n minus y factorial multiplied by p to the x multiplied by q to the n minus x. So let's break that down. And I'm going to take a second, rewrite that formula so we can have it for our reference. So we were interested in the probability of getting one success. So our sample size was 3. Our one success, that's our y value, which we can see written here. 1 factorial, 3 minus 1 factorial is 2 factorial. Our probability of success was 1/4. And again, our y, or so rather our x, is 1. 1 minus 1/4 is 3/4. And n minus x is 2. If you do not remember how we solve a factorial, so using 3 factorial as an example, that is equivalent to 3 times 2 times 1. If we are talking about 5 factorial, that would be 5 times 4 times 3 times 2 times 1. For this situation in general, we could have used the following binomial formula, where 3 choose x multiplied by 1/4 to the x multiplied by 3 over 4 to the 3 minus x, where x equals 1, 2, 3, or 4, because those are our options for our possible outcomes. Let's take a look at a second example, because I understand that this has been a lot of information thrown at you. The probability that a patient recovers from a rare blood disease is 0.4. If 15 people are known to have contracted this disease, what is the probability that exactly 5 survive? So as always, I do like to write out the information that we have. So we're going to let x be the number of surviving. Now, clearly, this is a success-failure situation. You are alive or you are dead. So this means that x is binomial with a sample size equal to 15 and a probability of success being 0.4. And we are asked to find the probability that exactly 4, so that's going to be x equals exactly 5. Using our formula, actually to start off with, I'm going to write this out generically. So recalling our previous formula, the probability of x equals x. Our sample size is 15. That would be 15, choose x, multiplied by our probability of success, which in this case is 0.4. This would be to the x. 1 minus 0.4 is 0.6. To the n, which is 15 minus x. Now, the reason I wrote this generically out, oops, sorry, this is the problem of having a touchscreen. So I wrote this out generically just so you could see where that x was coming in. So we're now asked to find the probability that exactly 5 survived. So in this case, x is equal to 5. So this would be 15, choose 5, multiplied by 0.4 to the 5th, multiplied by 0.6 to the 10th. Simplifying, this would be 15 times 14 times 13 times 12 times 11 divided by 5 times 4 times 3 times 2 times 1. Multiplied still, 0.4 to the 5th, multiplied by 0.6 to the 10th. This would be simplified to 3003 multiplied by 0.4 to the 5th and 0.6 to the 10th, which would give us a probability of 0.1859. Now, generally when we're finding probabilities of probability distributions, we round to 4 decimal places. And that's it. That is the probability that exactly 5 survive. Let's extend this. So what is the probability that less than 10 survive? So in this case, it would be the probability that x is less than or equal to 10. Now, in this case, our formula provides for a situation of exactly x equals x. So what you're going to have to do is you're going to have to do a summation, in this case of x equals 0 to 9, where our sample size is 15 and our probability of success is 0.4. Now, there is two ways we can do this. One way is to do it directly. That is to do the summation of x equals 0 to 9, 15 to the x multiplied by 0.4 to the x, 0.6 to the 15 minus x. And if we did that, that would be 0.9662. You can do this, that is perfectly valid. There is another option, and that is to use the binomial table. Yes, this is on eCampus. So what the binomial table does is along the y-axis, you will have your sample size and then your number of values of interest, and along the x-axis, you'll have your p. Something to be aware of in this case is this gives the probability of x less than x, meaning, so we were asked to find, or excuse me, yeah, less than or equal to x. And so in this case, our sample size was 15. We wanted to know less than 10, so that would be less than or equal to 9. And our probability of success was 0.4, so our probability of interest was 0.9667. And I apologize, I just realized now I had blocked the wrong box, but the answer is correct. It is 0.9662. That will be something I'll have to fix in the future. Now, using these tables, yes, it is on eCampus. As I said before, it does provide the probability of x less than or equal to. In your textbook, it says r. Obviously, the formula itself says x. For the binomial random variables for specific values of n and p. For discrete random variables, let me remind you that the probability of x less than or equal to r is not equivalent to the probability of x less than r. So in our previous problem, it said to find the probability of less than 10. Well, less than 10, you can't have partial lives, so that means the next one is 9. So less than or equal to 9 was our R value. Pay attention when you're reading. Think smarter, not harder. When we're dealing with continuous variables, obviously that's not the case, but when it's discrete variables, this is a very important rule to remember. So now that we have introduced the probability distribution and the wonderful table, let's do another example. So now we'd like to know what is the probability that at least 3 but no more than 8 survive. So once again, we still have the same sample size of 15, and our probability of success is 0.4, probability of failure is 0.6. Now, we have been asked to find the probability of 3 less than or equal to x less than or equal to 8. Once again, we do have the option of finding this directly, that is doing the summation of x equals 3 to 8. 15, choose x, multiplied by 0.4 to the x, multiplied by 0.6 to the 15 minus x. Or we can use the table. When we use the table, remember it does the probability of x less than or equal to x. So what we are going to do as an alternative, we would find the probability of x less than or equal to 8, and we would subtract the probability of x less than or equal to 2. That way, using our table, we can find the probability that we need. Going back to our table. Okay, so erasing the previous stuff now. taking a look for our problem. So our numbers of interest were 8, still 0.4 probability. So that would give us probability of x less than or equal to 8 to be 0.9050. And really what we wanted was from 3 to 8. So we need to subtract off that probability of x less than or equal to 2, which is 0.0271. So once again, we found from our table the probability of x less than or equal to 8 to be 0.9050, and the probability of x less than or equal to 2 being 0.0271. So this will give us a probability of 0.8779. So the probability that at least 3 but no more than 8 survive is 0.8779. Pretty good. Okay, so as I said, there are specific formulas that we memorize and know in response to our various probability distributions. Naturally, each of these have their own specific mean and variance and special notation. So when we are talking about the binomial notation, we tend to write it as our variable of interest, let's say x, tilde, bin, abbreviation of binomial, and then in parentheses, n comma p, and as our sample size, p is our probability of interest. How we say this technically is that the random variable x follows or has a binomial distribution with n trials and probability of success p. When we are using our binomial distribution, our mean, which we abbreviate sometimes as E of x, or meaning expected value of x, is your sample size multiplied by your probability of success, and your variance is your number of trials multiplied by the probability of success multiplied by the probability of failure. Notice, of course, then that your standard deviation would be the square root of NPQ. So let's just consider this at a moment. So still using our probability distribution for the binomial distribution, let's practice finding the mean and the variance. So let's consider the probability distribution where 3 choose x with a probability of success of 5/8, probability of failure being 3/8. 3 would obviously be our sample size. So this would be x following the binomial distribution with 3, 5/8, and our q would be 3/8. So if we were interested in finding our mean, that would then be 3 times 5/8, or 15/8, which we would then simplify to 1.875. Now to find the variance, using our information from the previous slide, it would be 3 multiplied by 5/8 multiplied by 3/8. That would equal 45/64, and that would be equivalent to 0.703. Very good. Not too bad. Let's do another one using our previous example. So once again, the probability that a patient recovers from a rare blood disease is 0.4. If 15 people are known to have contracted the disease, let X be the number of patients who recover. So once again, this is going to be our X is going to follow the binomial distribution with n being 15 and our probability of success being 0.4, and we can see that our probability of failure would be 0.6. Our formula for finding the mean is n times p. So this would be 15 multiplied by 0.4. So this would mean that our mean is equal to 6. So we should expect that 6 patients should recover. Our variance is n times p times q. So that would be 15 times 0.4 multiplied by 0.6, and that would be 3.6. I will say a lot of the problems with the probability distributions are reading a situation and knowing which distribution to use and then keeping all the formulas in your head straight. It may be useful to you to have a piece of paper where you record each of the distributions, their characteristics, and then their corresponding formulas. It would be helpful to have a cheat sheet, in my personal opinion. Okay, let's take a look at another example. It is conjectured that an impurity exists in 30% of all drinking wells in a certain rural community. Suppose 10 wells are randomly selected and 6 are found to be contaminated. If the conjecture is correct, what is the probability that we would find 6 or more impure wells? We will let X be our number of impure wells, and we can tell that X is going to follow the binomial distribution. We're looking at successes and failures. Our sample size is 10, and our probability of success in this case is 30%. So in this case, we wanted to find, we wanted to find what is the probability that we would find 6 or more impure wells. So in this case, we were asked to find the probability of X greater than or equal to 6. Now, the thing about finding the probability of X is greater than or equal to 6, once again, you have two options. You can find this out directly by finding the probability of X equals to 6 plus the probability of X equals to 7 plus the probability of X equal to 8 plus probability of X equal to 9 all the way to probability of X equals to 10. That is, of course, rather inconvenient. So our best option is once again to use the binomial distribution table. The issue with this, of course, is that it gives you the probability of X less than or equal to X. So we have to employ our use of the complement rule. So the opposite of the probability of X greater than or equal to 6 is 1 minus the probability of the probability of X less than 6. Remember, 6 is included, which means when we're doing its complement, we need to exclude it. So it will be really the probability of X less than or equal to 5. Using our binomial table, then we would have a simple lookup situation, n equals 10. Our probability of success equals 0.3. And our parameter of interest then would be 5, our value of interest. And so therefore, the probability of X greater than or equal to 6 would be 1 minus 0.9527, which would give us a probability of 0.0473. So therefore, in conclusion, it is very unlikely that 6 or more wells would be impure if the true contamination rate was 30%. In fact, it would only have a 4.73% chance, so not very high. And once again, just looking at the table, where did I get that value? We had a sample size of 10. We were trying to find the probability of X less than or equal to 5, which we would then subtract from 1, and our probability of success was 0.3. Okay, so that brings us to the end of our discussion on the binomial distribution. Just to sum up, a Bernoulli trial you can think of as a single event. When we are looking at multiple events put together, then it becomes a binomial situation. This brings us to our third distribution of interest, which is the Poisson distribution. And this also has an extension to the binomial distribution, or at least a connection, although right away it's not always obvious. So when you have an experiment in which you count the number of outcomes during a particular time interval or a specified region or space, we consider that to follow the Poisson distribution, such as the number of phone calls received per hour, number of snow days during the winter, or the number of typos on a single page. So we say that the number of X outcomes during a Poisson experiment is called a Poisson random variable, and then its distribution is the Poisson distribution. So there are a couple bases of our Poisson experiment. First, the number of outcomes occurring in one time interval is independent of the number that occurs in any other separate time interval. In other words, the Poisson process has no memory of previous events. It only pays attention to the current event of interest. Next, our probability that a single outcome will occur during a very small time interval is proportional to the length of the interval, and that the probability that more than one outcome will occur in a very small time interval is negligible. Now, for the Poisson distribution, it introduces a new parameter, which is lambda. So we let t be some specific time, distance, or area of interest. Our lambda is the average number of outcomes per unit of time or distance or area. Our mean, our expected value, is going to be lambda times t, and it is the average number of outcomes for a specific time or distance or area of interest. So for example, if we were talking about the number of phone calls you receive in 2 hours on average, well, the time would be 2 hours. The average number of outcomes per hour might be 5, so the average over 2 hours is 10 phone calls. Now to formally define our probability distribution. The probability distribution of a Poisson random variable x, representing the number of outcomes occurring in a specified time interval or region denoted by t, is denoted as a lowercase p in parentheses x, which is our random variable, semicolon lambda t, which is equivalent to e to the lambda t multiplied by lambda t to the x over x factorial, where x equals 0, 1, 2, and so on. Again, lambda is the number, the average number of outcomes per unit of time, distance, or area. As I stated before, our mean when dealing with the Poisson distribution is lambda t. What is very special about the Poisson distribution is that it is also equivalent to the variance. So at this point, let's go ahead and take a look at an example. The average number of radioactive particles passing through a counter in 1 millisecond is 4. What is the probability that 6 particles pass through in a given millisecond? So we let x be the number of particles in 1 millisecond, and we notice that x has a Poisson distribution with lambda t equal to 4. And then again, that would be the 4 times 1, because t is our 1 millisecond and 4 is our lambda. And we were asked to find the probability of exactly 6. So the probability of x equal to 6, plugging into our formula, that would be e to the negative 4 multiplied by 4 to the 6 over 6 factorial. This is a simple plug into your calculator situation, and we'd have a probability equal to 0.1042, or in other words, the probability is about 10%. Now, there is actually a Poisson distribution table If we wanted to use that in this situation, we would be welcome to. In that case, just like in the binomial distribution, the table does the probability of x less than or equal to x. So in this case, we'd have to do the probability of x less than or equal to 6 minus the probability of x less than or equal to 5. And that would still give us our probability of 0.1042. And here is a picture of the table, where the probability of x less than or equal to 6 is 0.8893, and the probability of x less than or equal to 5 is 0.7851. And notice the expected value, our average, is at the top, which for us is 4. The Poisson table is not as commonly used as the binomial table, but it is still provided for you on eCampus. And as you can see in this situation, using the table does not save you any work. By the time you would open up the table, write down your two numbers and subtract them, you could have just found the probability exactly, but it is still good to know how to use both methods. Okay, so let's take a look at this example continued. So let's find the probability that no more than 5 particles pass through in 2 milliseconds. So now we have a new random variable y, which is the number of particles in 2 milliseconds. So in this case, still y would follow the Poisson distribution with a lambda t of 4 times 2. Our lambda is still 4 because it is still 4 particles in 1 millisecond, but our t has altered to be 2 milliseconds. 4 times 2 is 8, and we are asked to find the probability that no more than 9 particles pass through. No more means less than or equal to, so we are going to try to find the probability of y less than or equal to 9. We could calculate this directly by doing the summation of y equals 0 to 9 of e to the negative 8 multiplied by 8 to the y over y factorial. That would equal 0.7166. Or we can use the Poisson table. Our lambda t is 8. We want to find y less than or equal to 9. And from the table, we would get the probability of 0.7166. In this case, I would have recommended using the table because finding those probabilities exactly and then adding them together would take more time than using the table. And in my opinion, it's all about efficiency. Now, as I stated earlier, there is a relationship that exists between the Poisson and binomial distribution. And so that is that if we have x that has a binomial distribution with parameters n and p, if your sample size is very large and your parameter of success is close to 0, then the Poisson distribution, where our mean is n times p, can be used to find the probabilities about x. So stated more clearly, if you have a binomial situation, so successes and failures, but your sample size is very large and the probability event of interest has a very small chance of occurring, we can use the Poisson distribution instead. So let's take a look at an example of this type of situation arising. In a certain industrial facility, accidents occur infrequently. It is known that the probability of an accident on any given day is 0.005, and that accidents are independent of each other. What is the probability that in any given period of 400 days, which is a little over a year, there will be an accident on one day? All right, sorry. I was thinking that that was going to have the answer on the next slide. Okay, so clearly x follows the binomial distribution with n being 400 and our probability of success being 0.005. But this does align with the situation I talked about on the previous slide with a small p and a large n. So instead, we are going to use the Poisson distribution with our mean being NP, or in other words, 400 times 0.005, which is equal to 2. Now we can go ahead and answer our question. And asked us, what is the probability that in any given period of 400 days, there will be a single accident? So what is the probability of x equal to 1? Using our formula, this would be e to the negative 2, 2 to the first over 1 factorial, and this would be equivalent to 0.2707. So there is a approximately 27% chance that within 400 days that there was a single accident. But let's extend this example and say, what is the probability that there is at most one day with a single accident? Meaning we want to know what is the probability that x is less than or equal to 1. Now in this situation, I don't mind calculating it out directly because it is really just finding the probability of x equal to 0 and adding it to the probability of x equal to 1, which we've already calculated so far. So this is going to be e to the negative 2 multiplied by 2 to the 0 over 0 factorial. If you don't recall, 0 factorial is equal to 1, plus e to the negative 2, 2 to the first over 1 factorial, which we've already found. And this would be 0.1353 plus our previously found probability of 2707. So this would give us a probability overall of 0.4060. So the probability that there was one or less accidents in this factory is 40.6%. Not bad. I'm sure they wish it was better, but still overall, not bad. Okay, so that brings us to the end of our discussion on discrete probability distributions. At this point, we're going to move on and talk about the continuous probability distributions. So to begin, there are 3 characteristics of the probability distribution that is of interest to us, and that is that the graph of the distribution is usually a smooth curve, which makes sense because it should be graphed out continuously. And the total area under the curve is 1. This is that equivalence to the summation of our probabilities in the discrete probability distributions being equivalent to 1. And that the area between the curve and the horizontal axis from the value A to the value B represents the probability variable taking on the value in the interval from A to B. And so what we're talking about is if, say, this was our distribution and we were interested in the probability from event A to B, this area corresponds to the probability. Now, a couple differences between the discrete and the continuous distributions. The most important difference that we really care about, and I addressed this earlier, that is in the continuous distributions, the probability of A less than X less than B is equivalent to the probability of A less than or equal to X less than or equal to B. And same thing, so the probability of X less than or equal to A is equivalent to the probability of x less than a when we're dealing with continuous distributions. Of course, that is not the case when we are dealing with discrete distributions. So those were the big things I wanted to talk about as far as the continuous distribution in general. For the remainder of this lecture, we are going to talk about two specific continuous distributions, the continuous uniform distribution and the normal distribution. So the continuous uniform distribution is incredibly basic. It is an excellent way to start out. It is simply the function equal to 1 over b minus a, where we're interested on the bounds of a less than or equal to x, less than or equal to b, and it is 0 otherwise. And what this looks like is it actually forms a rectangle with a base from b minus a and a height of 1 over b minus a. So suppose we have x being the uniform distribution on the bounds from 1 to 3, then our f of x would be equivalent to 1 over 3 minus 1, which would be 1/2. Again, this is on the bounds of 1 less than or equal to x less than or equal to 3. And here on the slide, we have a nice image of the uniform distribution. It really is a rectangle, and our area of interest is simply the area of this box. And again, the area under the quote curve should be equal to 1, and we can even check that out. 1, 2, 3, so this would be 2 by 1/2. 1/2 times 2 is equal to 1. So the area equals 1, and that checks out, and that should be the case. So a little couple facts about the uniform distribution. The mean, when we're using the uniform distribution, is a plus b over 2, and the variance is b minus a quantity squared over 12. So if we're using our first example, the mean would be 2, 3 plus 1 over 2 is 2, and the variance would be 1/3. Let's do a quick example. Suppose the length in hours of meetings in a particular conference room has a uniform distribution on the interval from 0 to 4. What is the probability any given meeting lasts at least 3 hours? Now, there are multiple ways that we could calculate this. One way would be to use calculus. We can tell that f of x is going to be 1 over 4 minus 0, which will equal 1/4. And this is on our bounds from 0 to 4. So, as I said before, one of the options is to use calculus, and that would be to do the probability of x greater than or equal to 3. And we would integrate from 3 to 4 of 1/4 dx, and that would equal 1/4. This course is not considered to be calculus based, but I did want to give you an FYI. The alternative for us, though, is to simply draw a picture. So we are on the bounds from 0 to 4. We know that f of x is equal to 1/4. And if we are trying to calculate the area, then we can see that the area from 3 to 4, because it's at least 3 hours, but no more than 4, would be 1/4. So in this case, I would definitely recommend drawing the picture out if you are not familiar with the calculus. Okay, so the continuous uniform distribution is pretty short to talk about. What we're about to talk about, the normal distribution, is not short. Of all the distributions in statistics, the normal distribution is the most important. I think we have about 20 slides left in this presentation, and it is all dedicated to the normal distribution. I cannot emphasize enough how important this distribution is. It will be referenced a lot for the remainder of this class. Oftentimes, we assume that our samples are drawn from a population that is normal. So, talking about the normal distribution, now you get to see your first image of it. It is a bell-shaped distribution that describes many phenomena in nature, and it is the basis of much of the statistical theory. As I said before, it is something that is going to be brought up quite frequently for the remainder of this course. It is characterized by two parameters, that is the mean and the standard deviation sigma. Some textbooks use the variance. Just be aware when you're reading problems, as always, to see whether you're given the information on the variance or standard deviation. So defining the normal distribution properly, the probability density function for a random variable x with a normal distribution with mean mu and standard deviation sigma is f of x equal to 1 over the square root of 2 pi multiplied by sigma, all multiplied by e to the negative 1 over 2 sigma squared multiplied by the quantity of x minus mu and quantity squared on the bounds from negative infinity to infinity. And we would write x follows the normal distribution with mean mu and standard deviation sigma as x, comma, or not comma, excuse me, tilde, capital N, and then parentheses are parameters of interest. I am not going to ask you to calculate probability using this function. That does require calculus, and that is not the focus of this course, but I felt for completeness I did need to show it to you. There are thankfully other non-calculus ways in order to find probability for the normal distribution. So just to talk about some nice properties and to enhance your knowledge of the normal distribution, as we can see here, we have two normal distributions with different means and the same standard deviation. So notice that they have an equivalent distance from the mean, which again, standard deviation, when we're talking about the normal distribution, you can think of it not only as a measure of spread, but also as a measure of distance. So in this case, we were given an identical means, but in this case, we had two different standard deviations. In this case, the standard deviation 1 is smaller than the second standard deviation. The smaller the standard deviation, the smaller the distance away from the mean. And here's an example where we not only have two different means, but also two different standard deviations. In this case, our mu1 is less than our mu2, and our standard deviation 1 is less than our standard deviation 2. Notice that we are still looking at two bell-shaped curves that are unimodal and symmetric, but notice how our information changes. When we have a smaller standard deviation, more of our data is clustered around the mean. So there are some wonderful properties of the normal distribution. Our mode is going to occur at the mean. The curve is symmetric about a vertical axis through the mean. Inflection points occur at 1 standard deviation away from the mean, both to the left and the right, and it approaches the horizontal axis asymptotically as we move away from the mean. And as is a normal property of a continuous distribution, the area under the curve is equivalent to 1. And I realized I just used a term inflection point. That may not be something that you are aware of. So flipping back, actually I'm going to go back a couple slides to our first experience. So at this point here, which it was denoting as 1 standard deviation away from the mean on the graph, this is known as the inflection point. So from the top of our curve to the inflection point, our curve is going downwards. At the inflection point, our curve changes its shape. So before it was going down, and now it's more headed towards the right. That is the idea of the inflection point, is that it's where we have a sort of change in direction. Okay, so talking about finding the area under the curve. So I mentioned this already, and this is an extension of understanding the concept of continuous probability distributions. The area under the curve, total area, is equivalent to 1. When we're interested in specific sections, that is equivalent to the probability. If we were interested in using calculus to find the probability between two events, say x1 to x2, we could take the integration. As I've stated before, to solve this directly requires calculus. This course is going to focus on doing alternative methods, particularly using z-score. But one of the most basic methods to find areas under the normal curve is by using the 68, 95, 99.7 rule. And what this rule says is that approximately 68%, 95%, and 99.7% of data lies within 1, 2, and 3 standard deviations of the mean, respectively. And here's a nice visual representation of this. So between positive 1 and negative 1 standard deviations of the mean lies 68% of our data, within 2, 95%, and within 3, 99.7%. And this is a good thing for you to be aware of, is if you have a distance, we'll say, that goes greater than 3 standard deviations above or below the mean, that would indicate it is a very rare event, or, less than a 99.7% chance of happening. So let's take a second and try to find some probability using our 68, 95, 99.7 rule. So a test of depth perception is designed so that scores are normally distributed with a mean, mu, and a standard deviation of 10. And we'll let x equal the score. And we are asked to find what is the probability that x is less than 50. Now, in this particular case, finding the probability of x less than 50, we really don't need to use our 68, 95, 99.7 rule. In this case, we should be able to use logic. If I draw out my normal distribution, and I apologize, not perfect, we can see that our mean, mu, is 50. Now to move 1 standard deviation away, that is the mean, in this case, plus 10. So this would be 60 to the right, 40 to the left. And we could keep going on, but right now that tells us that, 68% of our data is between 40 and 60. But also we know that the mean and the median are equivalent when we are dealing with a unimodal and symmetric curve. So what is the probability that x is less than 50? Well, that's going to be 50. Our mean is our exact halfway point. That is our 50%. But now we actually are going to be interested in using our 68, 95, 99.7 rule, because now we're being asked to find the probability of x less than 60. Now we can see that 60 is here. On our graph. And we know from 40 to 60, it is 68% of our data. But what about everything else? Well, the total area under the curve is equal to 100%. We've eliminated 68% of it between 40 and 60. So that leaves 32% to be within our remaining tails. As this is a symmetric graph, that means we have to divide it evenly. Let me rewrite that a little neater. So that means that each of our two tails are going to have 16% of our data. And we are interested in knowing the probability of x less than 60. So that's going to include this 68% and the left tail, which is 16%, to give us a total area of 0.84 or 84%. Let's do two more. Once again, I'm going to draw out my normal distribution. I know that I have 50 in the center, 40, 30, 20, just for fun, 60, 70, and 80. All right, so in this case, we were asked to first find the probability of x is greater than 70. So x is greater than 70 is going to be this area under the curve. Once again, we can use our 68, 95, 99.7 rule. 70 is within that 2 standard deviations of the mean. So by using our 95% knowledge, we know between 30 and 70 lies 95% of our data. Now we just need to find out what's on the tails. So if we subtract 95 from 100, we have 5% to be split between our two tails. So once again, we'll divide by 2, and this will give us 2.5% to be on each tail. And look at that, that's exactly what we were curious about. So the probability of x being greater than 70 is going to be 0.025. Not bad. Now let's take a look at trying to find the probability of x is greater than 40. few seconds, do some erasing. Okay, now we're back in business. So we want to know the probability of x being greater than or equal to 40. Now, as we established in the previous slide, we know that 68% is within 1 standard deviation of our mean. So between 40 and 60 is that 68%. And from our previous slide, we learned that there was 16% on each of our tails. So in order to find the probability of x being greater than 40, we would add the 68% plus the 16%. And once again, the probability of x greater than 40 is 0.84. Still not bad, right? Let's take it up one step higher. This time, let's find the probability of 40 being less than x less than 70. And because I think it is the best way to go about it, I do like to draw the picture. "50 in the center, 1 standard deviation to the left and right is 40 and 60, 2 standard deviations, 30 and 70. So we were asked to find the area from 40 to 70. We know from now doing it multiple times, from 40 to 60 is 68% of our data, because that's within the 1 standard deviation of the mean. We now also are interested in knowing the area from that 60 to 70 to get that total area. What we can do is use a combination of our knowledge for the 68% being within 1 standard deviation of the mean and our knowledge that 95% of our data is within 2 standard deviations of your mean. So between 30 and 70 we know is 95% of our data. Between 40 and 60 is 68%. So if we take a moment and subtract, we can see that 27% of our data is between 30 and 40 and 60 and 70. If we once again cut it in half, we would see that each of our sections of interest are 13.5%. So now it is a simple addition. Our 68% plus that 13.5%, and that will give us a probability of 0.815 or 81.5%. A little more challenging, but definitely doable. This might be something that you may need more practice problems on, which if that's the case, either ask me or ask Lord Google. Okay, so now that we've gotten into finding the probability of the area under the normal curve, obviously that rule for 95, 99, or sorry, 68, 95, 99.7 rule isn't going to work in every situation. It works great, but it doesn't always work. So this helps us need to find a alternative option. So in order to do that, we need to have an understanding of the standard normal distribution. So a normal distribution can have any mean and any positive standard deviation. But there is a special situation known as the standard normal distribution, which is when the normal distribution has a mean of 0 and a standard deviation of 1. We often in statistics let the letter Z be used to represent the standard normal random variable. And we can see that pictured here. Now, areas for a normal distribution for a random variable y with any mean and variance are found by performing a simple transformation of origin and scale. And the transformation is as follows, where z equals y minus mu over sigma. So that's stated formally. Let me break it down a little informally. Sometimes in statistics, we are interested in comparing things with different units, say a track meet. Say we're trying to determine who is the best athlete at a track meet. Now, the problem is we have people doing the long jump and people running the 400-meter race. Well, long jump has a distance measure where those running have a time measurement. How could we possibly compare them? Well, with what we call the z-score, we're able to convert everything that comes from a normal distribution, regardless of the units, into the standard normal distribution. If you were thinking distance, it's converting everything to the metric system, churning, everything into meters. That's honestly what we do here is regardless of whatever mean variance that we were given originally, we can convert it into the standard normal distribution. And from the standard normal distribution, just as with the Poisson distribution and the binomial distribution, they had a special table. Same thing with the standard normal distribution. There is a special table that we can use to find the correct probabilities. Also, the standard normal distribution has some pretty nice properties that we as statisticians really like to use. And we'll get more into that later. But for now, let's focus on using our new z-score formula. So let's take a look at an example. So let us suppose that our value z follows the standard normal distribution with mean 0 and standard deviation 1, and we're interested in finding the probability of z less than 1.27. So this brings us to needing to learn how to use our z-table. It is posted in eCampus, or it is and can be found in the back of your textbook. How we would read it is along the y column is your first 2 digits for your z-table. So it'll have the value in the ones place and in the tenths place. And then the hundredths place is found along the x-axis. So we were asked to find the probability of z less than 1.27. So we would find the 1.2 on the left-hand side and then 0.07 at the top, and this would give us a probability of 0.8980. Just like the other previous tables, this does give you the probability of, well, in this case, not x less than or equal to x, but z less than or equal to z. And as is the other tables, the report does give you, or the table gives you your probabilities within 4 decimals. So let's take it a step further. So as I said before, this does give the probability of z less than or equal to our value. So when we looked up the 1.27 value, that gave us the area to the left of the curve, but we were actually asked to find the probability of z being greater than 1.27. So that means we have to bring in that wonderful concept of the complement again and subtract. 1 minus 0.8980 would give us the true area under the curve of interest, which would be 0.1020. Once again, let's take a look at another example. In this case, we want to find the probability of z being less than negative 0.52. As you saw in the previous slide, I do recommend, at least as you're getting started, to always draw the picture so you have a concept of what you're looking at, particularly when we're dealing with the normal distribution, because it can be pretty easy to draw and also very easy to get confused. So we were asked to find less than negative 0.52, so it's easy enough to draw a curve, 0 in the center, negative values going to the left, positive going to the right, and negative 0.52, approximately halfway between 0 and negative 1, and we're interested to the area of the left, to the left of our curve, which means we can pull our value directly from our z-table. We were asked to find the probability of less than negative 0.52, so this would give us an area or probability of 0.3015. Doing this one more time, trying to find the area between our A and our B. So this time we're asked to find the probability of negative 1.45 less than z less than 0.42. So just as we had to do before, because our table only gives us the area to the left of the curve, what we're actually going to have to do is find the probability of z less than 0.42 and then subtract the probability of z being less than negative 1.45. Because our first value will give us this total area that I've just highlighted in red. Let's see if this will let me change my colors. There we go. And the probability of z less than negative 1.45 would just give us this area that I've now highlighted in a darker red. So by subtracting, we'll get the area in blue, our area of interest. So using our table, we would find that the probability of z being less than being less than 0.42 would be 0.6628. And the probability of z being less than negative 1.45 would be 0.0735, which would give us a total area or probability of 0.5893. And just to show a nice worked out version of what I did by hand, you can see it below. So sometimes we do have to use our z-table in reverse. So far we've been finding areas under the under the curve from given values of z, but sometimes we do have to do this opposite, meaning we're given the area and then we need to find the corresponding z value or z-score. So for example, what is the value of z has 10% of the area under the curve greater than it? So once again, we're going to draw the picture out. So that means 90% is to the left and 10% is to the right because we want greater than. We know that our table is given to give us areas to the left of the curve. So we're going to try to find our Z table entry that is as close to 0.9000 or 90% as possible. Now, if we were to use our table, the closest we could get to would be a Z value of 1.28, which has a probability value of 0.8997, or 1.29, which is 0.9015. As the 1.28 is closer, we will let our C value be 1.28. If it's something that's like exactly halfway between and you want it to do 1.285, that's perfectly fine. I do grade your assignments by hand. So if you want to do something like that, that's okay. If it's obviously closer to one or the other, you know, do the 1.28. But if it's almost exactly halfway, then go ahead and split the difference. And just to see this visually, let's keep my ink, I'm going to pull up our Z table. And the Z table I am pulling up is the one on eCampus. So we were asked to try to find as close to 90% as possible. So I'm just trying to get to where we are at 90%. And here we are. And it is between the 0.8997 and 0.9015, just as on my slide. And so our values again, 1.2 and between 1.28 and 1.29. But I did want to show you it on the table itself. Okay, back to our slides to take a look at another example. So in this case, we want to find the 26th percentile of the standard normal distribution. So that would be the probability of Z being less than Z, that is equal to 0.26. So within the table itself, we're going to get as close to 0.2600 as possible. In this case, the closest we'd be able to get is to 0.2611. And so therefore, our Z value would be negative 0.64. And if we wanted to try to find what was the value of Z has 68% of its area to the right, well, again, our rule tells us that our area gives it to the left, not the right. So we're going to have to do the probability of not the 68%, but we're going to have to try to find as close as we can to the 32% from the table itself, because again, the table gives us to the area to the left, not the area to the right. So in this case, our answer is going to be negative 0.47. And I apologize, I feel like that did not come out as clearly as I would have liked it. So let's try that again. So the area to the right of the curve is what we've been asked. We've asked to find 68% to the right. Our table only gives us information to the left, so we have to use our idea of the complement, that 1 minus 0.68, which would give us our 32%. That's the value we're going to look at in our table to find our Z value of interest. Much better. So now let's take it the step forward and re-find our probability from earlier, this time using Z-score. So a test of depth perception is designed so that scores are again normally distributed with a mean of 50 and a standard deviation of 10, and let X equal our score. And we are again asked to begin by finding the probability that x is less than 50. So now at this point we convert using z-score. So z is going to equal our parameter of interest minus the mean divided by the standard deviation. So our parameter of interest in this case is 50. Our mean is also 50, and our standard deviation of 10 is 10. So 50 minus 50 is 0. 0 divided by 10 is 0. If we look this up in the z-table, we will get our probability to be 0.5000. And now we can do the same thing for our probability of x less than 60. Once again, we're going to find our z-score. So this would be 60 minus 50 over 10. So this would become 10 over 10, which equals 1. So really what we've converted this to be now, instead of finding the probability of x less than 60, we're now going to find the probability of z being less than 1. So again, I'm going to exit out of here. Yes, I want to keep my ink notifications, and we're going to look for 1. Take a moment. Let me erase my previous handwriting. And so finding exactly 1, thankfully for us, is not hard. 1.00. And so the area for this is going to be 0.8413. And since we're here, remember for our first part, we had 0, and that is exactly 0.5. So 0.8413. At this point, you may be wondering, when we did it earlier with the 68, 95, 99.7 rule, we got an answer of exactly 0.84. The 68, 95, 99.7 rule is approximate. It's not exact. So in fact, 68% is, so is actually not quite accurate, neither is 95%. So thinking of the rule, it says that 95% of your data lies within 2 standard deviations of your mean. It's actually not true. It's actually 1.96 is a closer value, but it is the closest value that we could get to 2 standard deviations, which is why that rule is an approximation and is really good when we're starting out, and if your values are almost exactly within 1 and 2 and 3 standard deviations. But when we have values in between exactly 1, 2, and 3 standard deviations, then we need to use the z-score, which is why we're doing this now. So let's continue. So I don't have to keep going back and forth. I am going to do parts 3 and 4 simultaneously. So for Z3, we want to find the probability of x being greater than 70. So still, this using our z-score, this would be 70 minus 50 over 10. So this would be 20 over 10, which would equal to 2. Our z4 would be the probability of x greater than 40. So this would be 40 minus 50 over 10. This would then become negative 10 over 10, which equals negative 1. So now going to set up our problem, we've now converted into the standard normal distribution. So our probability of x being greater than 70 has now become the probability of x being greater than 2. Now, as we know, the standard normal distribution table gives us areas to the left of the curve. So let's set this up now, knowing that we really are going to have to do 1 minus the probability of x less than or equal to 2. And we're going to have to do something similar for part 4. Instead of finding the probability of x being greater than 40, we're now going to find the probability of, oops, typo, these should be z's. The probability of z being greater than -1, or as we use our complement rule, the probability of z being less than or equal to -1. So at this point, I'm going to exit out of these slides and pull up our z table, and we're going to be looking for z values of 2 and -1. So for 2, that is going to be 0.9772. So 1 minus 0.9772. And then the probability of c being less than or equal to -1, let's find that. And that is going to be 0.1587. All right, going back to our full screen. Now we just need to do a little bit of math. So 1 minus 0.9772 is going to give us 0.0228. And then for our probability of x being greater than 40, that will be the 1 minus 0.1587, or equal to 0.8413, which we should expect because that was also an identical area on the previous slide. Okay, so let's wrap this up, finding our part 5, which is the probability of 40 less than x less than 70. So for us, when we're going to do this, just as before, we had to find the probability of x being less than 70 minus the probability of x less than 40. We're going to do our simple conversion. So this will really become the probability of z being less than 70 minus 50 over 10 minus the probability of z being less than 40 minus 50 over 10, which is going to equal the probability of z being less than 2 minus the probability of z being less than -1. Oh, what do you know? We did some of that on the previous slide, right here. So this is going to be 0.9772 minus 0.1587. Let me double check that value. Yes, okay. Now we can subtract to find our probability and area. So 0.9772 minus 0.1587 gives us an area of 0.8185, or 81.85%. Not bad, at least in my opinion. All right. So this brings us to the end of this video. I feel like we've got a pretty good working knowledge of our distributions. For you guys right now, you should go ahead, read chapter 2, sections 3 and 4. Keep working on your homework 2 and complete and turn in your third knowledge check. Have a good night, everyone. And if you have questions, please feel free to send me an email.